We mentioned the term formal charge earlier, now we're going to explain it. In certain instances, more than one feasible Lewis structure can be illustrated for a molecule. For example, HCl. We could have it with carbon as the central atom with a triple bond with nitrogen, or we could have nitrogen as the triple bond as the central atom. The concept of formal charge can help discern which structure is most likely. Now, in our instance, if you follow the rules I gave you, you would pick HCl with C being the central atom based on it being the least electronegative atom. But in some cases, you might need to do a structure and then analyze it to see which one is the better structure, and by doing formal charge, you can determine that. The formal charge of an atom is determined by using the following formula. Note, formal charge is not the oxidation number of the atom. Formal charge is dictated by how the structure is put together, by the number of bonds, etc. Formal charge is equal to F minus B minus 2 times L, where F is the number of valence electrons in the free atom, the neutral, not bonded to another atom. So basically, how many valence electrons does that element have? B is the number of bonded pairs attached to the atom. A single bond counts as 1, a double bond is 2, and a triple bond is 3. And L is the number of lone pairs around the atom. So how many lone pairs? As a pair, how many lone pairs do you have around the atom? The most likely structure is the one with the least number of atoms carrying a formal charge. Structures with small formal charges, such as 0, +1, -1, are more likely to be stable or significant than those with larger formal charges, such as +2, -2, etc. Structures where neighboring atoms have formal charges of the same sign are less likely to be stable or significant. If I got two atoms attached to each other and they both have the same sign, meaning both negative or both positive, that's highly unlikely. Okay? It's more likely when you have a negative next to a positive. If neighboring atoms have opposite formal charges, we would expect the more electronegative atom to have the negative formal charge and the least electronegative atom to have the positive charge. So if you have this plus and minus, you expect, if you look at the two, the least electronegative will be the more positive one, and the more electronegative will have the negative charge. Let's look at our example. So let's calculate the formal charge of each one of these. So let's look at the first hydrogen. We know that it has one valence electron. It has one bond, no lone pairs. So therefore 1 minus 1 minus 0 for the lone pairs equals 0. Carbon, 4 valence electrons. It has 1, 2, 3, 4 bonds, no lone pairs. 4 minus 4 is 0. Nitrogen. It has 5 valence electrons. It has 1, 2, 3 bonds. It has 1 lone pair. So 5 minus 3 and 2 times 1 gives me 0. Let's look at the next hydrogen. Valence electron 1, 1 bond, no lone pairs, 0. Nitrogen. Valence electrons 5. I have 1, 2, 3, 4 bonds, no lone pairs. 5 minus 4 minus 0 is a +1. Carbon, I have 4 valence electrons, 1, 2, 3 bonds, in 1 lone pair. So 4 minus 3 minus 2 is a -1. So now we're going to look at these two structures and decide which one makes more sense. In this case, the structure on the left, with just carbon as a central atom, is the most stable or significant one based on the least number of atoms carrying a formal charge. All of them have 0. The structure on the right is also not selected because the least electronegative atom, carbon, has a negative formal charge. So this is my least electronegative atom, and it has a negative charge, while my more electronegative atom has a positive charge. That doesn't make sense either, so therefore, for that reason as well, we would select HCl. Bond length, or bond distance, is the distance between the nuclei and a bond. Knowing the bond length in a molecule can sometimes give clues as to the type of bonding present. Covalent radii are values assigned to atoms such that the sum of the radii of the atoms A and B approximate the AB bond length. For example, to predict the bond length of carbon and chlorine, you add the covalent radii of the two atoms. So basically, the bond length is what we're saying here, is the distance from one nuclei to the other nuclei. We would take the radius of carbon plus the radius of chlorine, and that'll give us an estimate of the bond length between carbon and chlorine. Atomic radii tables allow the prediction of bond lengths. This gives us an approximate bond length with variations due to repelling and attractive forces. We define the AB bond length, denoted by BE, as the average enthalpy change for the breaking of an AB bond in a molecule in its gas phase. The enthalpy, delta H, of a reaction is approximately equal to the sum of the bond energies of the reactants minus the sum of the bond energies of the products. So your delta H is equal to your summation of your bond energy of your reactants, taking into account the number of the bonds that are being broken, minus the number of summation of the bond energies of the products, accounting for the number of bonds of each one that's being formed. In this process, when you break in bonds, you're absorbing energy. When you're forming bonds, you're releasing energy, so the sum of all that energy will give us our delta H of the entire reaction. If we absorbing more energy to break the bonds than we are forming, then we end up with a positive delta H. If we absorbing energy, less energy than we are forming bonds and releasing more, then we have a negative value. Note, this is the bond energy of your reactants minus your products. Okay, this is your reactants minus your products. This is the complete opposite of that, of what we had in the thermochemistry chapter. Let's illustrate this. Let's look at methane plus chlorine, giving us our CH3Cl and HCl. Okay. In this reaction, let's examine to see what's happening. We can see that one CH bond is going to break and one Cl bond is going to break. We have three CHs that are going to stay the same. They're not going to be broken. We're going to break this CH bond and we're going to form a CCl bond. We're going to break this Cl bond and then we're going to form that hydrogen that comes off this CH4 with that Cl, forming an HCl. So in this reaction, one CH bond and one ClCl bond must be broken on the reactant side, and in turn one CCl bond and one HCl bond are formed on the product side. We have to account for those. The three CH bonds that remain unchanged from the reactant side to the product side, we will not account for. They'd be the same. Okay, we could put it in the equation if we wanted, but it does cancel out. So we're going to ignore those three bonds. So we have to look to some tables and find the bond energies. And we find that CH is 411 kilojoules per mole, ClCl is 240, CCl is 327, and HCl is 428. So we know the delta H will be equal to the bond energies of your CHs plus the bond energy of your ClCl on your reactant side. Remembering that I would have to account for the number. If I was breaking two CHs, I would have to multiply this by 2, but in this case, everything is 1. That's my reactants. Then I'm going to subtract the bond energy to form my CCl and to form my HCl. Once again, if I had multiple bonds, I would have to account for those. Plug in the numbers. 411 for my CH. My 240 is ClCl minus my CCl is 327 and my HCl is 428. Do the arithmetic and I come up with a total of a negative 104 kilojoules. So this whole reaction is exothermic. It's releasing more energy to form the bonds than it's absorbing energy to break the bonds. Homework 67.